Namaskaram. Welcome to the next session of Svādhyāya 1.1. In this session, Dr. Soumya Dey will dwell into the main topic or the theme of Svādhyāya 1.1, that is, finitely generated abelian groups. Over to you, Dr. Soumya Dey.
Over to you. Yes, sir.
Thanks, Amlan, Ritoprovo, Manogna, and all other organizers. So before we begin today, I would like to hear from the participants their experience, okay? What they have learned in this 1 week about finite abelian groups, its structure, etc. So what exactly we have done so far? Can anyone give a brief summary? Yeah, anyone? What exactly we proved so far? Yeah, you can unmute and speak. Anyone? Okay, let me call names then. Jayasri, what about you? Right. So Astha, can you just tell us what exactly is the theorem, the fundamental theorem?
So basically, fundamental theorem says is that every finite abelian group can be expressed as the product of cyclic groups.
Right.
As internal direct product.
Exactly. So any finite abelian group is basically a direct product of some cyclic groups, okay, or cyclic subgroups if you are considering internal direct product, right? And what more can you say about these cyclic groups? What are the orders of these cyclic subgroups? What are the orders? These are prime powers, right? So we proved that if you have some group having some finite abelian group having some order, right? You just break it into different subgroups where each of them are having some power to the some n, right? Pi to the ni, right? So that's what we have done so far. So any group which is finite and abelian, let's take some example, okay? Suppose you have a group G which you know is abelian, okay? And suppose the order is equal to 200. Right? So I want to know how many such possibilities are there? How many such abelian groups are there having order as 200, say? Okay. So what we are going to do is we'll see the prime factorization of this 200. Okay. What is that? So 2 divides 200, right? What is the maximum power of 2 that divides 200? It's 8, right? So 2 into 2 into 2, that's 8, and then times 25, right? That is 5 into 5. So what you can write is 2 cube times 5 square. So the maximum power of 2 is 3. If you remember, in corollary 1, I guess, right? What was the corollary 1? So corollary 1 said that if you have some finite abelian group G, okay, and you have some prime P which divides the order of the group, then you can write G as P direct sum T, where P, capital P, is some subgroup, okay, which is of order P to the sum M. And the other subgroup T doesn't have, the order doesn't have any P factor. So P doesn't divide the order of T. That was corollary 1. Okay, so if you apply this here, you have some abelian group of order 200. Okay, what you can do is you can write this G as some product, okay, where my P, this P will have, okay, order as 2 cube, okay, and the other one, that T, mod T, will be 5 square. You can do that by this corollary, because this is the only way you can divide as P cross T, such that 2 divides, so that the mod P is 2 to the 3, and the other part, which is T, mod T doesn't have 2 as a factor, right? All right. And then we have seen in the fundamental theorem, right? What did we see? We can write this G as a direct product. Okay, there can be more than 2 copies now, each of them having, okay, having a cyclic group of some prime power. Okay, so this P that we have got here, that may not be cyclic, right? It may not be a cyclic group of order 8. It could be, it has 3 possibilities. If you look carefully, this P can be either isomorphic to Z8, or it can be Z4 cross Z2. What is the other possibility? The third possibility is it can be right, Z2 cross Z2 cross Z2. These are the 3 possibilities for P. I know the order is 2 cube, which is 8, but these are the 3 possibilities which P can, the structure of P can have. Okay. Similarly, what about T? T, I know that the order is 5 square, okay, but it may be cyclic, it may not be cyclic. So in case it is cyclic, this T will be isomorphic to Z25. Otherwise, T can be Z5 cross Z5. These are the only 2 possibilities, right? So if you combine all of these, okay, for G, how many possibilities do you have? Okay, let us see. So G can have 6 possibilities. What are the 6 possibilities? The first possibility is you have P as Z8 and T has Z25. Okay, so So this is one possibility for G. Okay, or the first one could be Z4 cross Z2. Second one, Z25. Third one, Z2 cross Z2 cross Z2 cross Z25. Okay, there are more, right? You can take Z8 cross Z5 cross Z5. Fifth possibility is Z4 cross Z2 cross Z5 cross Z5. And finally, you have Z2 cross Z2 cross Z2 cross Z5 cross Z5. Okay, no other possibility. Okay? These are the 6 different finite abelian groups of order 200. Okay, that's what we are getting. All right, you can take some other, instead of 200, you can take 300, 400. Okay, any number, any integer you can take, and you can try to come up with all possibilities. Okay, for example, you can take something like, let me give you one number. Okay, so suppose mod G is equal to say 2 to the 4 cross 3 to the 3, 5 to the 2. Okay, what will you do in this case? So the question is, you know that G is abelian. Okay, how many possibilities? But not just how many, but what are the possibilities? Okay, try to see this. Okay, now, so we have proved one version of this fundamental theorem of finite abelian groups, right? Let me just complete this. Okay, after this observation, what exactly we have proved? Let me write down. So every finite abelian group G is isomorphic to a direct product of cyclic groups, okay, such that, okay, for some integers, say n1, n2, up to nk, G is isomorphic to Zn1 product Zn2 product ... to Znk, where each of these ni's, okay, these are prime powers, right? That's what we have proved. So ni is equal to pi power, say, di, okay, where all of these pi's are prime and di's are some natural numbers. Okay, this is what we have proved. This is the fundamental theorem of finite abelian groups, the version that we have proved. But there is another version, okay, which is basically coming from this only, okay. Let us see what is that, okay. The other version is saying this, okay. I'll write down and then we'll discuss about that. It says every finite abelian group G is isomorphic to a direct product of cyclic subgroups such that for some integers k1, k2 up to say km, okay, what I'll say is G is isomorphic to zk1 cross zk2 cross zkm, where, okay, I'm not saying each of these ki's are prime powers, but what I'm saying is each ki is a multiple of ki plus 1. Okay, try to think what exactly it's saying. I'm not saying these ki's are prime powers. I'm saying k1 is a multiple of k2. Okay, k2 is a multiple of k3, and so on. So each ki is a multiple of the next ki plus 1. How can you say this? How can you make sense of this, given we have already proved the other version? Any ideas? Suppose you can find this structure, right? That your group is isomorphic to Zn1 product Zn2 dot product Znk, where all these ni's are pi to the di for pi primes, okay. How do you get the next form? Okay. So let us see. We'll take some examples and try to convince ourselves. Okay. So for example, you look at these. Okay. So these are all abelian groups of order 200. We have just seen. Okay. Now there is one result. I guess all of you know that. So let me just state it. And if you don't know, we can give some idea how to prove. Okay. So this is the result. So this statement is, so proposition. What this says is this. If you take two cyclic groups, Zn and Zm, if you take the product, direct product of Zn and Zm, this will be isomorphic to the cyclic group of order n times m. Okay, if and only if Can anyone say when it will be?
The GCD of N and M is 1.
Very good. So GCD of N and M is equal to 1. Okay. So this is a standard theorem in group theory, right? So how do you prove this? Suppose your your GCD of N and M is 1, okay, and you have to prove that Zn cross Zm is isomorphic to Znm. What you have to just show is you have some element in this group Zn cross Zm whose order is n times m, and the element could be 1, 1, right? So 1, 1, which is in Zn cross Zm, what is the order of this? So this is, suppose this is K, okay, all right, but the meaning of order is what? This is the least K such that if you, so in this case the operation is addition, right? So you add 1, 1 K times, you will get 0, 0. So that's that. So basically this implies that K, K is equal to 0, 0. This means that both M and N, they divide K, right? So this implies what? N divides K and M divides K. But this will say that since our GCD is 1, right? This means what? This means the LCM is actually equal to this says that our K is equal to the LCM of N, M, and that's it, right? This will LCM of NM, you know, since GCD is 1, this is equal to N times M. So you have found some element 1, 1 which has order which is equal to the order of the group, and hence this generates your group as a cyclic group, right? So this proves the one way. The other way is again simple. So you have suppose your Zn cross Zm. So conversely, suppose this Zn cross Zm is cyclic of order n times m. So this has some element, right? Some element say a comma b of order n comma nm, right? N times m, which is the order of this group Zn cross Zm. And now we have to show that the GCD is 1. What you find from here is if you consider these two elements, say a comma 0, and you take the cyclic subgroup generated by this is actually equal to this Zn cross singleton 0. And similarly, 0 comma b, the cyclic subgroup generated by that, will be equal to singleton 0 cross Zm. Okay, and you just see this, that order of AB, since a comma b is equal to a comma 0 plus 0 comma b, right? And you want in both, so you want to add AB sufficient number of times so that both the entries become 0, and that will happen if both the first one becomes 0 as well as the second one becomes 0. And to do that, you just need the order to be the LCM of these two, right? So order of a comma 0 and the order of 0, comma b. But the order of a comma 0 is n, and the order of 0 comma b is m, right? Okay. And but then LCM of nm is equal to nm in this case, because I've assumed that the order of AB is nm. So we have assumed the order of AB is nm. Implies LCM of nm is nm, but that will say GCD of nm is equal to 1. Yeah, so this is not difficult. So if you apply this, okay, if you apply this proposition now to our setup, right? Let's go back. So you have these groups, right? These groups of order 200. Now look at the first group. It's Z8 cross Z25. Okay. Okay. Using the proposition, what you can say? Since 8 and 25, their GCD is 1, this is nothing but Z200, right? Right? Let us see. So this Z200, it's already in the form of the second fundamental theorem, the second version, right? What we want in the second version, I want to express the group G as some product of Z K1 cross Z K2 cross dot 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 Z Km, such that the first one, which is K1, is a multiple of K2. K2 is a multiple of K3 and so on. So in this case, the first group Z is Z200. So there is only one term. Okay, let us see the next term. Then it will be clear to you what exactly is going on. So what I'll do in the second one is you have Z4, then Z2, and then Z25. Now, among these first two, okay, Z4 and Z2, I'll look at the highest order of 2, which is appearing here. So highest order of 2 is 4, which is Z4. And in the second part, the highest order of 5, there is only 1, so it's 25. So I want to merge these two. So Z4 and Z25, okay. Since this is an abelian group, you can rearrange these terms, okay. So Z2, you can put this Z25 in the middle. That is okay, right? You can understand since this is abelian. So what I'm saying is, you have this Z4 and this Z25. So Z4 cross Z25, since 4 and 25 are co-prime, the GCD is 1, you can club them. And what you get is you have Z100, and then you have a Z2 left. Okay. And this is in the form that I want in the second version. See, 100 is a multiple of 2. Let us see the next. Here I have two, there are 3 groups coming from the prime 2, okay, the power of 2. So you have Z2, 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 and then you have Z25, which is coming from the power of 5. I'll look at the highest power of 2 appearing here, which is 2, and the highest power of 5 appearing. So I'll club, say, this Z2 and this Z25. So again, they're co-prime. So I'll say this is isomorphic to Z50 cross Z2 cross Z2. Okay, and you see again 50 is a multiple of 2 and 2 is a multiple of 2. Let's do quickly the next ones. So you have Z8 and Z5 here. So the largest power here is 8 and largest power of 5 is 5. So you club these two, you get Z40 times Z5. The next one you have, so the first is you have, so you look at the largest power of 2, which is 4, and the largest power of 5 is 5. So this Z4 and Z5 you can club. And from the remaining, again you see the largest power in the remaining. So Z2 and again Z5, these two can again be clubbed. So what you are getting is Z4 and Z5 will give you Z20. Product with Z2 and Z5 will give you Z10. Okay, you see what is happening? So again, 20 is a multiple of 10. What about the last one? So among these 3 Z2s, you can take one Z2 clubbed with one Z5. Similarly, the second Z2 with the second Z5 and one Z2 will remain. So it will be Z10 cross Z10 cross Z2. So all these groups are expressed as a product of ZK1 cross ZK2 and so on, where Ki is a multiple of Ki plus 1. Okay, so you understand this algorithm, and by doing this exactly same procedure, you can do with any group. Once you have it in one version, you can just transform using this algorithm and you get the second version. All right, so that's something that we should note here. So there are two versions we have understood now, right? So okay, all right, any questions? If not, let us move to the next or last segment of the talk. So you see, whatever we have done so far, everything was about finite abelian groups. But you should wonder, we have given the name of this event, Svādhyāya 1.1, as finitely generated abelian groups, right? So what is the meaning of finitely generated abelian groups? Finite abelian groups you have understood. But what is the meaning of finitely generated abelian groups? Okay, let us define that. What is the meaning of finitely generated? Okay. So suppose you have a group G, any group. It can be, maybe abelian, may not be abelian, right? So we'll say that, any question? Let me see the chat. No.
Sir?
Yeah, tell me.
As you say, we can write the abelian group Z200 in 6 ways. But the above
Right.
result showed that we can write the abelian group in more than 6 types.
No. See, the rules are different. So in case of the first way of writing, okay, let me go back. Yeah. Here, whatever you are seeing on the left, what is the rule? Here, each of these groups, they are of prime power. Do you see? Z8, 8 is a prime power. Z25, 25 is also 5 square, right? Prime power. But whatever you are getting in the right hand side or the other way of writing, these are not prime powers. For example, Z50, it's not a power of a prime, right?
But sir, in
Okay.
the definition of finite abelian group, there is not any mention of the power should be a prime number. So the number should be a prime number.
Where definition means statement.
Actual, yes, sir. Actual sir, the statement says that the finite abelian group can be written as product of cyclic groups.
Right.
It
But
does
if
not
you
say about what is the order of the cyclic groups.
right. So if you go to the, as I said, can you see the statement of corollary 1? What is the statement of corollary 1 that we proved?
Yes.
Yeah.
It is said. It
So it
says
says if you start with any finite abelian group, you can write that as a, so given any prime p, you can find a way of writing G is equal to P cross T, where P is of some prime power, that P power, and T, the other side, okay, that the order of that doesn't have any P in it. Do you see that? So
yes.
P doesn't divide mod T. What does it mean? So you're basically writing the group as this capital P is the maximum possible power of small p that you can have. You are separating out. And then in the remaining part, say capital T, there is no power of p. It's the order has no p in it, but it will have some other primes. For example, in this case, if you look at the group with having 200 elements, right? There will be some subgroup which will be of order 8. Once you separate that, the remaining part is having some 25 order, right?
Yes.
So
Yes.
basically what you have done, you have broken your group into two parts, both of which are having prime, the order is some prime power. And if there are more than two primes, you can do the same. You can apply again this corollary to the capital T. Suppose some Q is another prime which divides mod T. What you can do is you can separate out a part, okay, which is some, the order of that part will be Q power something, and remaining part will doesn't have any Q in it. So in this way, in finite steps, what you can do is you can write your group as a direct product of different cyclic groups where each of them are having prime powers. The order is prime power, different primes, not the same prime. Okay,
Yes. Thank you.
so that is the idea. Yeah. All right. So this is, so you have now these two different versions of fundamental theorem is giving you different ways of writing. Okay, if you restrict to one of the rules, there are only 6 ways. There are only 6 different non-isomorphic finite abelian groups of order 200, namely these 6. But then if you change your rule, you don't want each component to have prime power, but you want that the ki should be a multiple of ki plus 1. If you insist on that rule, then on the right hand side also we have achieved other ways of writing these 6 groups. Okay, all right. Now let us understand what is the meaning of a finitely generated group. Okay. Suppose you have any group. It may not be finite. Okay. So it can be non-abelian also. Any group, suppose you take capital G, and you have some subgroup, say S. So S is a subgroup of G. Okay. What is the property of capital S? The property of capital S that we are looking for is, for every small g in capital G, any element you pick. Okay. So for any small g in capital G, what you can do is you can write this G as a product of elements from S. Okay. So what I mean is, you can write this as some S1, S2, S3 up to say Sn. Okay. In fact, I can allow the power to be either +1 or -1. So some of these can be inverses also. For example, it can be so instead of S2, I can have S2 inverse. Okay. So what I mean is, any element in the group G can be written as a product of elements from S or their inverses. Okay. So I'll write it. I'll write it as this. So I want G to be S1, S2, Sn, where these SIs belong to either S or in S inverse. What is the meaning of capital S inverse? I'll collect all inverses of elements in S. That's the meaning. What is an example? For example, you take Z. Z is a group. Okay. You can take S to be singleton 1. Right? Any element you take, okay, if n is positive, you can just add 1 n many times. Otherwise, so this is if n is bigger or equal to 0. If n is less than 0, what you can do? You can write n is equal to -1 plus -1 and so on. So inverse of 1, you can add sufficient number of times, namely -n times. You can write any element of Z as a sum of 1s or -1s. Clear? But there are more examples. This S is not unique. Okay, you can have some other S. You can take S to be 2, 3 also. Why? So I'm claiming that any integer can be written as a sum of 2, 3 and their inverses, namely -2 and -3. Can any one of you tell me why this is true? For example, say, how do you write 4? 4 can be written as 2 plus 2. Easy. Yeah, because GCD is 1. Very good. What about 5? 5 can be 2 plus 3. What about -1? -1 could be 2 plus -3. Right? You understand what I'm doing? So you can just try, okay? So any element of Z, if you take any integer, you can find some combination of these 2, 3 and their inverses, and you can write that element as a sum. So if you have such a scenario, if you can find some such S, some subset of your group, you say that this S is a generating set for your group. Okay. So in such a scenario, we say G is generated by S. Or S is a generating set for S. For G, sorry. S is a generating set for G. Okay. Now, when do you say a group is finitely generated? The most natural definition is if you can find some set which is finite, okay, and it generates the group. Okay. So this is the definition of a finitely generated group. So G is called finitely generated if there exists some subset S G such that S is finite and G is generated by S. Okay. Now, we are concerned with finitely generated abelian groups. Okay. Okay. So these are abelian groups having some subset as a generating set which is finite. Okay. So some examples are, what are some examples? We have already seen Z is finitely generated, right? Because you have singleton 1, which is a finite set, and that generates Z. What about any finite abelian group? Right? Any finite group is definitely finitely generated, right? Why? Suppose G is a finite group. So mod G is less than infinity. It's finite. What can you take S to be? Very good. It generates itself, right? So S can be G. You take all elements to be your generating set. Easy, right? So any finite group is finitely generated group. So you have a lot of examples. Now, our interest is now what are some infinite groups which are finitely generated. One example is definitely Z. Okay. Can we have some more examples of such infinite groups which are finitely generated? How can you construct such abelian groups? Yeah. How about you take Z and you take direct product with Z5? Is it finitely generated? Why is it finitely generated? What can be a finite generating set for this? Singleton 1. What do you mean by singleton 1? So it's a direct product. So any element will have two components. It's an ordered pair, right? Yes. So any direct product of any two groups, okay, that is generated by. So if you have two cyclic groups, say G1 and G2, and you take direct product, right? You know that there is some element, say A, which generates G1, and there is some element B, which generates G2. If you take A comma identity and identity comma B, these two elements always generate the direct product, right? So similarly here, you can take these two elements, right? So one is the 1 comma 0, which is, so 1 is from Z and 0 is from Z5, and the other one could be 0 from Z and the 1 in Z5. These two elements will generate, right? Okay. Of course, there can be some smaller uh, generating set also. You just try to find if it's there. Okay. But now, how do you generate more such finitely generated abelian groups? Okay. So there is a fundamental theorem of finitely generated abelian groups, which says what are the precise, says precisely what are the groups, what are all possible such groups. Okay. So let me write down that statement. We are not going to prove that. Okay, that's beyond our scope. But this is the statement. Okay. So this is the fundamental theorem. On finitely generated abelian groups. What is this saying? This is saying that let G be a finitely generated abelian group, then there exists some R, okay, which can be a natural number or 0, and some elements. How do I write those? Say K1, K2 up to Km. Okay, these are all natural numbers, such that our group G is isomorphic to you have R many copies of Z. So if I write Z to the R, what is the meaning of Z to the R? This means Z to the R is you take R copies of Z and you take direct product. Okay. Okay, that's the meaning. So this says that G will be isomorphic to Z to the R product with some finite abelian groups, some direct product. So you will have some ZK1 cross ZK2 and so on to ZKM. And you can impose the condition of the second version, let's say. Okay, what is the second version for this part will tell me that I can put Ki is a multiple of Ki plus 1. So I can write this group, which is a finitely generated abelian group, as a product where one part is basically some product of Z's. Okay, and the remaining part, this is called the torsion. Okay? This part is called the torsion or the finite part. Okay, any element in this, if you take, the order will be finite, right? So this is called the torsion, and the torsion part will be, because it's a finite abelian group, we know the finite and the fundamental theorem for finite abelian groups that says that it has this structure, right? You can write it as a ZK1 cross ZK2 dot ZKM, where K1 is a multiple of K2, K2 is a multiple of K3, and so on. Okay, so this part is coming from there. The interesting part is you can have some copies of Z. So any such finitely generated abelian group will have this structure where one of the components will be some power of Z, some copies of Z, direct product, and then some torsion part. And the torsion part will have this exactly same structure coming from the fundamental theorem for finite abelian groups. Okay. So this is the statement, and now you know that what are all possible such groups, finitely generated abelian groups. You can take. Okay, now it's easy, right? So you take how many? So say 2 copies of Z, and you take some, say Z8 and some Z25. This is one group, right? And you can play with all these. You can have some copies of Z and then some finite part. So these are all possible finitely generated abelian groups. There are no other. Yeah. So if there are any questions, we can answer those, and otherwise we are stopping here. Thank you. Is there a specific reason it's called torsion? Yeah, I don't know the reason behind the nomenclature of torsion. Yeah. Maybe I'll look up.
Any other question from the participants? Okay, so I guess there is no questions. So let us all thank Dr. Soumya Dey for the great, awesome lecture he gave, and
Thank you.
also I will like to thank the participants because they also attended the session from the very beginning. Okay, so someone has raised hand.
Yeah, Tapan.
Sir, can you say what is the set who gendered the group as you write there? Z cross Z8 and Z25.
What is the set which generates?
Yes, sir.
Oh, that is easy. So for each of these component, so for example, this Z, if you look at this Z, okay, for this, what you will get? You have this 1, 0, 0, 0. Okay. For this Z, you can have 0, 1, 0, 0. By the way, so the first two components are coming from Z, and the next two components are coming from, so the third one is coming from Z8, okay, and the last one is coming from Z20. I hope you understand, right? And then you take 0, 0, 1, 0, and finally 0, 0, 0, 1.
Yes, sir. I think the others number will be take the identity. So I ask. Like here we take the number one who generated Z, and then we took the other parts as their identity. Like
Yeah,
zero zeros.
identity,
Yes.
identity meaning 0. Yeah, yeah. So this will generate your group. This can be S. Okay, so whenever you have a direct product, you can do this. For each component, you just take the generator for that component and put others as identity. Okay. All right. Any other questions?
Yes, if there is any other question from the participants, please ask. I guess now it's finally, yeah. So
Right. Yeah.
thank you, Dr. Soumya, for this lecture,
Thanks for
and
the
also to the
opportunity and the
uh,
patience of the participants. They have managed to complete this 1 week program. That's a good start. I hope we will have more such programs in future and they will participate. Yeah. Okay.
yes. I also thank the participants for participating in Svādhyāya 1.1, and also to the mentors and